Stand at the foot of any great American city and look up. The skyline is a museum of decades, a stacked timeline of steel and glass, each tower a testament to the engineering philosophy of its era. But look closely, and you'll notice something strange, something no one ever tells you. The oldest towers, the ones built in the 1930s, 40s, and 50s, stand proud with their original frames still remarkably intact. Their steel bones, hidden behind limestone, brick, or curtain walls, remain straight, strong, uncompromised. Buildings like the Empire State Building, the Chrysler Building, and 1950s mid-century giants across Chicago and New York are still structurally impeccable. But newer buildings, ones less than 30 or 40 years old, are already facing massive corrosion issues. Engineers open up modern facades and find rust blooming across beams, connection failures beginning decades too soon, and water infiltration quietly eating away at structures expected to last a century. How did the mid-century giants do it? Why does 1950s skyscraper steel still stand firm while modern skyscraper steel, built with more advanced metallurgy, more sophisticated calculations, and supposedly better protective coatings, rusts far earlier? Were engineers in the 1950s simply luckier? Were materials inherently better? Or is there a deeper truth, something uncomfortable about how construction has evolved? To solve this mystery, we have to step into the steel mills of 1950s America, descend into blast furnaces hotter than volcanoes, walk the scaffolds where riveters hammered steel into place under the open sky, and compare their philosophy of durability with the race-to-the-bottom incentives of today. And once you understand the answer, you'll never look at a skyscraper the same way again. To understand why mid-century steel has survived decades of rain, snow, salt, pollution, and time itself, we need to look at how that steel was made. Because 1950 steel wasn't just a product, it was a process. And every step of that process left fingerprints on its durability. Every beam, every column, every plate that rose skyward carried with it decades of careful engineering, scientific observation, and human craftsmanship. In the 1950s, American steel mills were at their peak. The United States produced more steel than any nation on Earth. Blast furnaces towered over the factories like metallic cathedrals, glowing with molten iron that flowed into molds and converters. They operated day and night, fueled by coke, limestone, and ore hauled from the vast mines of the Great Lakes. The air itself was thick with heat, sparks, and the smell of sulfur, a living reminder that industrial America was producing a product unlike anything seen before. Steelworkers weren't just laborers. They were craftsmen who understood the material like a living organism. They knew how steel flowed when molten, how it cooled under different temperatures, and how even a small misstep could create microscopic weaknesses that might take decades to show up. Their hands, their eyes, and their intuition guided the metal through processes that, to an outsider, might have seemed chaotic, but to them were a precise choreography of science and experience. The first major difference between then and now was the purity of the raw materials. The iron ore mined during the mid-century boom was incredibly high-grade hematite, remarkably low in sulfur, phosphorus, and other impurities. This gave steel a natural resilience to corrosion and fatigue. Modern steel, by contrast, is often produced from recycled scrap metal, efficient and cost-effective, yes, but a patchwork of alloys and trace elements. Copper, tin, and other residuals can subtly undermine corrosion resistance if not meticulously controlled, and in real-world conditions they often aren't. The purity of the 1950s steel created a chemical stability that modern fabrication rarely matches. But purity was only the beginning. 1950s steel was also thicker. Not metaphorically, literally. Plates, beams, and columns were produced with generous cross-sections, designed to carry loads far beyond what calculations suggested was necessary. Engineers and regulators weren't obsessed with shaving off every ounce of metal to meet optimization targets. They understood that overbuilding created forgiveness, thermal stability during hot summers, resilience against pitting corrosion, and structural integrity when exposed to unexpected stresses. The skyscrapers of that era didn't just meet building codes, they exceeded them in ways modern structures rarely attempt. Then there were the coatings, a critical, often overlooked layer of protection. In the 1950s, steel was coated with primers containing red lead, a pigment, now banned for environmental and health reasons. These primers didn't merely sit on the surface. They chemically bonded to the steel, forming a barrier that was nearly impervious to moisture. The protective layer created by these coatings slowed corrosion for decades, a feat modern paints and primers struggled to replicate even with contemporary chemical engineering. And finally, the assembly. Rivets and heavy bolts were more than fasteners. They were sealing systems. Riveted connections were heated, inserted, and hammered until they shrank tightly around the plates they held together. Each connection became a joint that was effectively sealed from water intrusion. Modern welds, while faster and cheaper, are inherently more prone to microscopic pathways for moisture, and in today's high-speed construction world, perfect execution is more an aspiration than a reality. In every step, from ore extraction to riveting, 1950s steel reflected a philosophy that building wasn't a temporary exercise. Skyscrapers were not designed for a few decades of use or for the minimal lifespans dictated by cost constraints. They were built for the ages. Durability wasn't a feature. It was the default assumption. Every structural decision, every ounce of extra steel, every painstaking rivet, every chemically bonded coating was a conscious investment in permanence. And that philosophy made the bones of those skyscrapers nearly immortal, standing tall long after many modern buildings have already succumbed to rust, decay, and structural compromise. Walk onto a 1950s construction site, and you'd feel something modern sites have lost entirely. The pace was deliberate, almost ceremonial. Workers spent days preparing a single connection, aligning beams with patience, checking every rivet, every bolt, every weld until it was perfect. Every element of the structure was approached as if it were a legacy, a permanent mark on the skyline. There was pride in the process, a sense that what they built would outlast them, their children, even the city around them. That slowness wasn't inefficiency, it was quality. Every beam lifted into place, every girder hoisted, every column welded or riveted was the product of a culture that valued permanence over speed. Time was measured in months and years, not in deadlines and cost savings. Workers learned to read steel like a living material, to feel its stresses, to anticipate how it would bend under weight, to understand the thermal expansion that might creep into a connection months after installation. The men and women who built these skyscrapers weren't racing against hyper-tight schedules or lean budgets. Projects often took years, and no one expected any different. When an engineer requested heavier beams, additional bracing, or thicker coatings, they weren't met with resistance or cost objections. They weren't asked why. They were asked, how soon do you want it delivered? The culture of construction in the 1950s assumed that safety, durability, and excellence were never optional. They were foundational. Contractors chose thicker coatings, more redundant connections, and more robust assemblies because the cultural mindset was simple. You build it once, and it stands for generations. Every layer of protection, every extra bolt, every rivet driven into place contributed to a structural system that was forgiving, resilient, and remarkably resistant to time. The buildings were armored against the elements, against mistakes, and against the unforeseen stresses of a century of use. Contrast that with today. Modern projects operate on margins so thin that every hour saved matters. Every kilogram of steel cut, every shortcut taken, Every lighter beam or faster cure time is celebrated as innovation. Value engineering, the practice of trimming costs and material, dominates design decisions, often without fully considering how these choices will manifest decades later. And the consequences of those decisions rarely show themselves immediately. A shortcut that seems harmless today can reveal itself as a structural weakness 20 years down the line, long after the building has passed inspection and the contractors have moved on. But buildings are brutally honest. A rushed connection will eventually reveal itself. A weld performed on a humid day can corrode from inside, creating tiny channels for water that accelerate deterioration. A cheaper primer may flake, exposing the underlying steel to oxygen and moisture. A facade, designed for a 30-year lifespan, will funnel wind-driven rain into the frame, slowly eroding connections and structural members. These are small failures that accumulate, silently, until the building requires major renovation, or worse, replacement. 1950s skyscrapers were overbuilt, not because engineers lacked knowledge of efficiency or optimization. They understood those concepts perfectly, but they didn't want to optimize at the cost of longevity. Their philosophy was clear: add more steel, make coatings thicker, use methods that take longer but last longer. They designed not just for the next inspection, but for decades of unrelenting weather, usage, and time. Every decision reflected a commitment to permanence, a belief that infrastructure should serve generations, not quarters. And it shows. After 70 years, when engineers peel back the cladding of a 1950s structure, they often find steel in astonishingly good condition, sometimes so pristine that it looks like it was installed last week. Rivets remain tight, beams remain straight, and corrosion that modern engineers assume inevitable is barely visible. That's the result of deliberate slowness, generous margins, and unshakable craftsmanship. Construction isn't just about materials. It's about mindset. And the mindset of the 1950s was uncompromising. Every rivet hammered, every connection aligned, every beam measured and remeasured was a statement. We are building not for today, not for 10 or 20 years, but for the ages. And that philosophy, slow, heavy, deliberate, precise, is why these skyscrapers still stand, even as many modern buildings crumble under the weight of time, neglect, and optimization gone too far. If the 1950s represent the golden era of durability, then the mid-1970s onward mark the beginning of the corrosion crisis. A slow, creeping problem that few noticed until buildings began aging faster than anyone expected. At first, it was subtle, small streaks on a beam here, a rusty bolt there. But over a decade or two, the problem became impossible to ignore. Skyscrapers designed to last a century were showing signs of failure before their first half-life. Several forces collided at once, creating what engineers now call the perfect storm of corrosion. First was the rise of welded steel construction. Welding promised speed, efficiency, and lower labor costs. Beams could be joined without dozens of rivets or hours of bolting. But welding changes the steel at a microscopic level. The intense heat creates heat-affected zones, areas where the crystal structure of the steel is altered, making it more susceptible to corrosion and cracking if the weld isn't executed perfectly. Even a small imperfection can become the seed for rust to propagate, and in modern construction, with compressed schedules and massive crews, perfection is rarely achieved consistently. Second was the shift toward lightweight design. Engineers in the 1970s and 80s began to calculate structures to the exact minimum strength needed. Gone were the generous margins of mid-century buildings. A 1950s beam might be 30% stronger than necessary, forgiving small losses of material over decades. Modern beams? Cut close to the theoretical limit. When corrosion eats away just a few millimeters, that safety buffer disappears, and the integrity of the building begins to degrade far more rapidly. What might be a minor inconvenience in a mid-century structure becomes a structural emergency in a modern one. Third was the globalization of steel supply. In the mid-20th century, steel came primarily from domestic mills. Ore, coke, and limestone, all controlled in a tightly managed process. By the late 1970s, steel was sourced from all over the world. Different suppliers, different alloys, and trace elements meant that corrosion resistance could vary widely between batches. Modern steel is still incredibly strong, but its performance in corrosive environments depends heavily on the exact chemical composition, and that composition is now less predictable than in the days of the Edgar Thomson works. Fourth was environmental regulation. The heroic primers and industrial coatings of the 1950s, red lead, zinc-rich paints, thick industrial lacquers, were phased out for health and environmental reasons. What replaced them was safer, yes, but also far less durable. Modern coatings protect steel for years, but they need maintenance cycles, periodic recoating, and careful monitoring. In practice, these maintenance requirements are often ignored or underfunded. Skyscrapers left to fend for themselves in urban environments quickly develop weak points where water and pollutants penetrate. And finally, there was architecture itself. Modern facade systems, glass curtain walls, and complex cladding assemblies often trap water or condensation in hidden cavities. Moisture sits against steel frames for years, slowly accelerating corrosion from the inside out. Older buildings with thick masonry cladding, ventilated cavities, and generous detailing allowed structures to breathe, to dry naturally, to shrug off rain and humidity rather than trap it. Put all of this together, and you get the corrosion crisis. Buildings not even 40 years old begin showing serious decay. Engineers routinely open facades from the 1980s and 90s to find rust so deep it must be scraped away in thick flakes. Some structures require full recladding. Others demand structural repairs far sooner than anyone anticipated. It's not that modern steel is bad. It's that modern construction asks the material to perform under conditions it was never designed to handle, with margins too thin, coatings too weak, and maintenance too often deferred. The same laws of physics apply, but the way we ask steel to perform has changed dramatically. If 1950s steel was a tank, built to endure decades of abuse without complaint, modern steel is a scalpel, precise, efficient, and impressive, but far less forgiving. Both have value. Both serve their purposes. But only one survives the tests of time, pollution, and timidez, and human neglect. And in the race between durability and efficiency, the mid-century skyscrapers have already proven they were built for the long game. Around the early 2000s, engineers began inspecting major mid-century skyscrapers for retrofits, facade updates, and new mechanical systems. What they found stunned them. They opened walls expecting corrosion, pitting, and the typical wear that decades of weather bring. Instead, they found steel almost untouched by time. Beams coated with red lead primer that still clung to the metal as if freshly applied. Riveted joints that remained tight, clean, dry. Columns that should have been weakened showed almost no section loss. In Chicago, renovation crews working on 1950s office towers were shocked at how little corrosion existed even after 60 winters and constant exposure to industrial pollution. In New York, engineers analyzing mid-century skyscrapers discovered that the limiting factor for future lifespan wasn't the steel. It was the outdated electrical systems, mechanical equipment, and facades. The structure, the thing that should have decayed first, was often the part in best condition. Some engineers even joked, "We could leave the steel, demolish everything else, and rebuild around it." The 1950s giants weren't just aging well, they were aging almost too well, surviving decades past their expected lifespan. But when inspectors turned to buildings from the 1980s or 1990s, the contrast was brutal. Corrosion where water had infiltrated, welded joints beginning to crack. In some cases, Steel so compromised that entire sections had to be rebuilt. Buildings younger than their inspectors needed unexpected structural repairs. The secret wasn't magic. It was overbuilding, quality craftsmanship, and materials made without compromise. The skyscrapers of the 1950s were built like fortresses, and today their durability is stealing the spotlight from buildings half their age. So, what can we learn from this? Should we return to old methods, old coatings, old materials? Should we abandon optimization and build everything thicker, heavier, slower? In a perfect world, maybe. But the economics of construction have changed too dramatically for that. Cities demand speed. Investors demand low cost. Regulations discourage materials once considered essential. And global competition makes slow, heavy construction hard to justify. But that doesn't mean we can't bring back the philosophy. The biggest lesson from the 1950s is that durability is engineered, not discovered. It doesn't happen accidentally. It happens when three things align. First, material quality must be tightly controlled. If steel is recycled, it must be monitored with the same rigor used in the mid-century mills to ensure purity and performance. Variability cannot be allowed to hide within the frame. Second, connections must prioritize long-term resilience over short-term cost. Riveting won't return, but modern bolted connections and improved weld inspections can fill the gap, if schedules allow them to be done correctly. Third, protection systems must be restored to a level of seriousness. Maybe we can't use lead primers, but we can choose thicker coatings, more frequent maintenance cycles, and envelope designs that ventilate rather than trap moisture. Finally, we must confront an uncomfortable truth. The rush to build fast has consequences that only time can expose. Buildings are not smartphones. They cannot be optimized to the bone and still expected to outlive their creators. A structure designed to stand a century must be built with a century in mind. And in the 1950s, that was exactly the mindset. So the next time you walk through a city and look up at the skyline, remember this. The towers built in the middle of the 20th century remain strong, not because they were lucky, but because they were built in an era when durability was a moral value, a promise to future generations. The rust creeping through modern buildings isn't a failure of steel. It's a failure of philosophy, a failure of priorities, a failure of an industry that once embraced permanence but now accepts planned obsolescence. And yet the 1950s giants tightened. As silent teachers, their rivets, their coatings, their thick beams, and their time-tested stability whisper a truth modern builders too often forget. Strength is not engineered by cutting corners. Longevity is not born of speed. And a skyscraper is not just a project to be completed. It is a legacy, a landmark, a future inheritance. The old skyscrapers still stand because they were built with reverence. Modern skyscrapers struggle because they are built with efficiency. And the skyline itself is telling us which philosophy wins. In another 50 years, some modern buildings may already be replaced. But the steel skeletons of the 1950s? They will still be there, holding strong, defying time, reminding us that durability is a choice. And once you understand that, you begin to see the city and its future in a very different light.